Okay, so I just want to do some little illustration regarding how to determine the endemic equilibrium points of an epidemiological model, right? So this is because sometimes beginners to modeling often have difficulties finding endemic equilibria of models, especially those of them that are nonlinear or they use nonlinear um, forces of infection, like we have in our model beta id plus epsilon tau t plus I out of n divided by n. Okay, so this is a model that was proposed by one of my MPhil students. I just want to try to explain how the endemic equilibrium can easily be found, right? Sometimes it is easy or it's possible for one to find explicit expressions for the endemic equilibrium. Other times, because of the nonlinear nature of the model, you may not be able to find uh, explicit expressions for that. However, there's an easy way to go about it, and so I'll just try to illustrate that in this episode. But to start with, it's often easier as you try to do computations with models of this nature. Um, the size of your expressions would often get uh, grow, and so in order to simplify that, you can often just let some compound parameters, set those ones to simple parameters. For example, we could set theta ed plus theta I plus mu to a single parameter, let's say k1 in that order. So we are going forward, we are just going to set mu s plus mu to maybe k1, and then alpha 1 plus mu to k2, then this expression to k3, this one to k4, tau plus mu to k4, and then tau I plus delta plus mu to k5 in that order. So let's do that. So we're going to set mu s, right? So we're going to go here and set mu s. So we are going to set conventions. Okay, see that the following conventions the following conventions are going to be used in the rest of the analysis, right? Okay, so we are going to set let k1 to be equal to mu s1, and then k2 we're going to let k2 to represent the next set of parameter sums, that's alpha 1 plus mu, right? So that's going to be alpha 1 plus mu. Then k3 is going to be theta ed, right, plus theta I, then plus mu, right? And then the k4 is going to be tau plus mu, then k5 is going to be tau I plus delta plus mu, then k6 is going to be equal to phi 1 plus phi 2 plus rho plus mu, right? And that is this expression there, right? And then finally k7, right? So k7 is going to be equal to alpha 2 plus mu r plus mu, right? So so with this convention, right, with this convention, the model is going to become something like whatever we have here. So we're going to just copy this whole expression, the whole model, this model, we are going to set all of that, and then in place of this compound sums of whatever sums of parameters, we can have, so just copy this one and replace the last expression here is k7, so put k7 there, right? And this expression is going to be k6, and then this expression is k5, then this one gives us k4, and then this gives us k3, right? And then this gives us k2, and then finally alpha mu s plus mu gives us k1. And so we have something like this. What is that? There's an error. What is that error? It's saying that epsilon treated k7. So we're going to have here, this is correct. This is that theta k and k4 tau mu, and then sorry, this is going to be equal to k5, right? Sorry, I left out k5. K5 is going to be this, so that's correct. And so we have all of these expressions. K7 is alpha 2. Sorry, let me end it here. So we're going to have this expression. So K1, K2. Sorry, this is not supposed to be K1. This is supposed to be K2, right? So we correct that, and then we have this expression. So we have K1, K2, K3, K4, K5, K6, and K7. So with that, all of these ones also become something like this. And also sometimes, because of the nonlinear nature of the force of infection, it often makes it very difficult for one to be able to find the endemic equilibrium explicitly. And so as a way around it, you can set the force of infection, in this case beta I ed plus epsilon t plus I over n. You can set that to some parameter, say m. So if we set that expression to say m, that is here, right? Okay, so if we set that to m, if we set that to m, if we set this one to m, so we can then replace, so in place of this we can put m there. So in place of that force rate of infection, we can put ms there, right? And then in similar manner, we can put msc inside here. So that is in the expression of E, right? So that's going to have all of this one times as ms. And so we have this expression. So now you will notice that the number of equations are going to be 7, and the number of unknowns are going to be 7 plus the m, which gives us 8. And so it should be easy for us to express those 7 variables in terms of maybe one of them, say m. And that is what we are going to seek to do at equilibrium. However, we know that at equilibrium, all rates of change are always 0. There's no change at equilibrium, and so we have to set all the rates of time derivatives to 0. And so I just copy this and paste it inside here, and I change all of the rates to 0. I change all of these rates to 0. 0. 0, change this to 0, 0, and then finally this should also go to 0. So now we have these equilibrium equations that are given by this. And so in order to differentiate your model variables from their equilibrium find values, we often would superscript this model variables at equilibrium by, let's say, epsilon, sorry, asterisk, right? So we're going to have asterisks out of these variables. I'm just copying and pasting. I'll just copy it. So I'm pasting against each of the model variables so that we are going to be looking for the endemic equilibrium points. So we set this to all of this. So that's, and then we have that. So if I run it, I'm going to have to write all of this. So let me just set the M to the star, right? So then we'll have M star, S star. Where is that? Where is that? Where is it? I'm going to have M star, S star. So we have all of this. And so we now have our equilibrium equations in terms of the 7 model variables and then our new variable M star M. And we notice that for some of those equations, those of them that have two unknowns, right? We can normally start with those ones and express one in terms of the other and substitute into some of those equations that will allow us to continuously simplify. So, for example, we are going to take the last equation, which we can use to find R star in terms of that T star. And so I copy this expression, right? And so I say that from this expression, we are going to have to, we can actually find R star, right? We can just make R star the subject, right? So I'm going to have all of that. So I'm going to set this to 0. Okay, so just going to divide the left hand side by the right hand side, and so we have something like this. Okay, so from that expression we have whatever we have, right? From this expression we can find R star, right? We can find R star, and so we have whatever we have here. And so with this R star, we can use that to substitute into some of those expressions to be able to find. And for example, later on we can substitute it into the first expression, right, to be able to find S. Okay. So the next thing to do, we can look at maybe the counting from the bottom. We have 1, 2, 3, 4. The fourth equation, right? The fourth equation can be used to find express one in terms of the other. So I say that also from the fourth equation, we can find from the fourth equation we have this, and we then should be able to find IED in terms of ED, right? So we can find IED in terms of ED. Alright, so I'm going to have this expression. Okay, so we have this. Then better still, if you want to let the constants stand out easily, so we have something like this. So we have IED, and then going back, you notice that we have IED in terms of I here, and so also if we decided to use the third equation from the bottom, right? Third equation from the bottom, we know that we can find I in terms of E and T. We can find I in terms of E and T, and so we can substitute all of that into this expression, right? Okay, so from we can use the second equation from the bottom, right? Around, and then if we take that second expression from the bottom, we're going to take all of this expression and say that from the third equation from the bottom, we can find t actually, right? So we can find t, set that to 0. So that is going to be equal to whatever we have here, right? You can find t, right? You can find t, and that t can then be substituted, and that t is in terms of id, ied, and I, right? So we can substitute that into the third expression at the top, right? I do not normally like to write expressions in this nature because I'll be using the t star in other expressions, and so I'll be doing substitutions for eg and I. So if you leave it as just a numerator, explicitly like this, sometimes after substitution it becomes very clumsy. So factor out the 1 over k6 and leave the tau ed plus tau I stand alone. So I'm going to cut this expression. Then I'm going to have 1 over k6 multiplying tau t. So I have this tau id, right? So I'm going to rewrite it in this manner. So we're going to rewrite it this way so that I can later on substitute that. So we're going to substitute expression for t star, right? We're substituting it into the third equation from the bottom, right? That's 1, 2. Third equation from the bottom, this as this expression, right? So if we take that expression, what is it going to give us, right? So we have that, and so I take the expression for t star, copy it, and I paste it in place of the t. And so if we do that, we are going to have this. I'm going to have this. And so I just take the tau phi 1 and then multiply by the 1, and that gives us whatever we have here. So I just cut it and replace the 1 with this because phi 1 times 1 is phi 1, right? And so we have all of this. Now, however, we remember that IED was also expressed in terms of E, right? Also expressed in terms of E. And so we can put in place of E the expression for IED. Also, okay. Also substituting should give us, I just copy all of that and paste in the next expression, next line, and I'll copy the expression for IED, right? IED has been written as theta ED over K4 times E. So I come and put the expression for IED here, right? In place of IED, I will place it inside here, and I'm going to have my expression, this expression, right? I'm going to have this expression, and so okay, so it's this expression that we get. So we can see that we can now find I star in terms of E from this expression. Okay, first of all, we need to be able to group lifetimes and do whatever we want to do. Okay, so I copy this one, and I can do further simplification. I'm going to have this multiplying that, so I'm going to have the tau, where the tau is here going up to join the theta ED, right? And that gives us whatever we have here, right? And then we're multiplying through by phi 1 over k6, phi 1 over k6. If we multiply through by phi 1 over k6, right, that gives us whatever we have here, and then times tau 1 I over that. So that gives us this expression, right? Gives us this expression, and we can do away with the brackets and then group our like terms. Okay, and so we can put like terms together. So we're going to have factorize e star, and then I'm going to factorize e star to get whatever we have here, and then I star can also be factorized. So that's going to be plus tau 1. We can factorize I star, right? So we can remove this I star and then factorize it, right? So if we do that, we are going to have something like this. Okay, so let me take my tau I to join its counterpart as a numerator. So let's cut it. And so we have all of these. And so we can find okay, so we can just find just use this to find an expression for I, right? So we just take this to the other side and divide, and so that is I star is going to be equal to whatever we have here, right? Whatever we have here. We are taking this to the other side, and then, so we're going to have k, but how are we supposed to have k5 minus whatever we have? Because we're taking this to the other side of the equation, it then becomes negative. That's going to give us k5 minus whatever is here. That's why we would have to write it as this. Right. And so, like I said, as your computations grow bigger and bigger, you often will see that it's advisable to often be very economical with your space, and so you can let a constant that has grown like phi I plus whatever all over k5 minus whatever, you can let that be some parameter, let's say psi1, right? So if we set this full expression, okay, so if we set this expression, let's say psi1, okay, so if we set that expression to psi1, okay, then we are going to have then I star is just going to be equal to psi1 times E star, right? So we are going to have that simple expression. So we're going to have something like this. So we have found I in terms of E. We have found I in terms of E, okay, and then we have also find ID in terms of E, and then we had T in terms of ED and I. And so once we have ID and E and I in terms of E, we can actually express T in terms of E. So let's do that. We copy this expression, and so we are going to substitute the expressions for, I'm going to say that expressions for IED star and I star into that of D star should give us whatever we have here. So we are going to substitute, so in place of I, we put the expression there, which is psi1e, right? Which is psi1e. So we replace I star in terms of psi1e star, and then we had found IED. I found IED here. IED had been found to be theta ED over K4E. So in place of IED, we put this expression there. So I'm just copying and pasting. So it should be very easy. That's one thing I like about LaTeX. It's easy for you to work around your work. So we can factor out the E. If we factor out the E star, right? So that is going to be equal to E star is coming out here, right? E star is going to come out, and then we have this expression, right? We have this expression that we have, and so like I said, we can let the tau join expression up here. So let's cut this and place it there, and then so we have whatever we have here. So now what we have done is that we have I, we have T, we have I, and we have IED, all in terms of E, all in terms of E, and then we have found R in terms of T, and so once we have now have T in terms of E, we can find R in terms of E. And so we're going to say that if we substitute the expression for T star into that of R star, it should give us, so we have this is R star, and so we're just putting expression for T star right into it. So I'm going to copy it and place it and put it in place of the T star in the expression for R star. So if I do that, I execute, I am going to have this expression, right? I'm going to have this. So R now becomes whatever we have here, and so we can make this one rho over K6, K7, K6, right? Rho over K6 times K7. So that's going to give us rho over K6, K7. Alright, so all of that. And so that gives us this expression. If we want further, we can bring out the K4, right? We can bring out the K4. Okay, so we can bring out, this can be written further as K4, K6, because we are going to multiply, write this as a single fraction and can factor out the 4, and so that is going to give us whatever we have here times K4 times tau I K4, and then we can factor out the K4 to have this expression we have here, right? So we have that. So that is that. So going back to the equations, we see that we have found R in terms of E, we have found T in terms of E, we have found I in terms of E, we have found ID in terms of E, right? And so what is left here is we have T in terms of E, and then we have T in terms of E, and so here we can just find S in terms of E. And that is what we can do. So that if we find S in terms of E, we can find V in terms of E here, and then in that order, right? Okay. So from the last, but from the third equation at the from the top. So if we take this expression, okay, so I often want to avoid, because this M star is actually a force of infection, and at equilibrium that is normally 0. But if if we want to divide here, want to find S by dividing by M star, that means that at the equilibrium point, when the force of infection is 0, then you're going to have S to be undetermined. And so normally I want to avoid that by ensuring that I don't have a division by the force of infection, so that we'll have division by 0 in the end at this is free equilibrium. So we'll avoid using the third equation from the top, right? But what we can do is to so it means that we have three extra equations, right? three extra equations that we can use. Okay, so what we can do is to write V. We can write V in terms of S and R, right? But R is in terms of E. So in effect, we are writing V in terms of S and E. And so that if we write that in terms of S and E, we can put that inside the first equation, and then we'll be able to write to find an expression for S. Okay, so that's fine. But however, I think that I need to go for a break. I'll return soon. Thank you.